Alrighty, how are you guys doing today? Good. Cool. Okay, so today we're going to learn about resistance and digital multimeters. Last time we built the Bobots and they ran around on the ground and you guys programmed them and taught them how to navigate through the course and park themselves in the warehouse. So that was pretty cool. And today we're going to switch over and we're going to switch gears. We're not going to use the Bobot kits anymore. We're going to start playing with some other things. And I like to think that this is a very cool lab because this is the first time you don't have to believe what I'm saying anymore. You guys can actually, so far I've been telling you some things and talking about voltage and resistance and you just kind of had to take my word for it. But starting today, you guys are going to learn how to use some instruments and actually make measurements, and you can try things out from yourselves from now on. So from now on, you won't have to take my word for it. You won't have to believe me anymore. You can actually try it out yourselves. Okay? So what we're going to learn about is a little bit about resistance. We're going to talk about what it is, why it's important, and we're going to learn about the color codes that we use in order to mark resistors, and we're going to learn how to read those so that we can actually look at a resistor and tell, just by looking at it, what resistance value it has. We're also going to look at some meters. We're going to talk about what they are, why they're important, and then we're going to use those meters in our lab to measure resistance. So we're going to talk about resistance in class, and then we're going to measure it in the lab. We're also going to use the meters to check out a cable. So if you guys ever do anything with cabling or wires, you will probably have to check out those wires and make sure that they are functioning properly. That means that wires are connected to other wires where they're supposed to be, and they're not shorted where they're not supposed to be connected. So we're going to find out how to do those measurements today using our digital multimeter. Okay? So that's a brief overview of what we're going to talk about. Any questions before we get started? All right, cool. So then let's talk briefly about what resistance is. Remember, we talked in the past a little bit about electricity, and we said that there were three major factors that we're considering. Current was the amount of electricity that was flowing. We said electricity is really the movement of electrons. Current is how many electrons are flowing. So more electrons moving is more current. Fewer electrons moving is less current. So current was one of the things. Voltage was the force that was pushing these electrons. So the current was the movement of the electrons. The voltage was the force that was pushing them. And then resistance was the force that was making it difficult for the electricity to flow. So we can say that resistance is the opposition to the flow of electricity. So that's what resistance is. Why is it important? Why do we put resistors into circuits? Exactly, so that they don't get too hot. Remember, when electricity moves, it causes things to heat up. And if we didn't have anything in the way, we could have a lot of electricity flowing through our circuit and it would heat up the circuit. That could burn us. That could also damage components. And finally, it's just inefficient. It would run down our battery really quickly if we were just using too much electricity. So we have the resistors in the way in order to limit the amount of electricity that flows and precisely set the amount of electricity that we want. Okay? So that's why resistors are important. Any questions about that? Okay. So, oh yes, I'm sorry.
The question is, how exactly it works on a molecular level? Just an idea where it's really...
Right, so what happens is that at a molecular level, remember, you've got the nucleus of an atom, and then all around that nucleus you have these electrons that are floating around, and they are orbiting the nucleus. And when you have lots of atoms packed closely together, you have more nuclei over here, more electrons over here, and what happens is that different elements have different properties. So some elements hold on to their electrons very tightly, and other elements don't have a very tight hold on their electrons. The elements that hold on to their electrons very tightly make it difficult for those electrons to jump from one atom to the next. So those elements are called insulators because they reduce the amount of flow of electricity. The elements that make it easy for the electrons to jump from one atom to the next, those are called conductors because they allow the electricity to flow more easily. So with a good conductor, you can take an electron and push it on over here, and that one bumps this electron over to here, which then bumps this electron over to the next atom, and so on. And they just hop from one atom to the next like that. So that's what happens in good conductors. With insulators, the insulating material wants to hold on to the electrons that they have. So it doesn't want to accept electrons from anybody else. It just wants to keep the electrons that it already has. So it makes it difficult for the electricity to flow. So you've got conductors, which make it easy for the electricity to flow. You make insulators, which make it difficult for the electricity to flow. And the way that we actually create resistors is that you take a blend of conductive material and insulating material, and you blend it up together. And then they form it into a little tiny package, and that becomes your resistor. So if they want a bigger resistance, they put in more insulating material to make it harder for the electricity to flow. If they want a smaller resistance, they put in more conductive material, which makes it easier for the electrons to flow. So that's how that's how resistors actually work on a molecular level. Yeah?
So my question was exactly like the conductors.
Right.
They're made from different material, let's say copper, aluminum,
right,
gold, silver, platinum, the best.
Right.
The which is expensive.
Right.
So, and they heat up. Why are they heating up? Like, the question is what resists to the flow of the electricity? Is it atoms, or are they close to each other, molecules, or there's no answer for this question?
I'm sure that there is an answer. I don't know exactly what it is.
Okay.
So that's a good question. Exactly what causes the heat, I don't know.
Sorry.
No,
I was just
it's
curious.
fine. No, it's a good question. But yeah, I don't know the answer to that.
Thanks.
Mm-hmm. Other questions? Okay. So we want to be able to look at the package of a resistor and determine how much resistance it has. So you might think that you could just look at the package and it would, if it was a 470 ohm resistor, there'd be a little number that says 470. It seems like the easy way, right? Well, we don't do anything easy in electronics, so they didn't do it that way. Instead, what they did is they created these little color bands that go around the outside of all the resistors. And it's actually the colors that specify the amount of resistance that you have. So each color represents a number, and there's a chart, let me show you what that is. So, yeah. black is 0, brown is 1, red is 2. Okay, so the colors are black, brown, red, orange, yellow, green, blue, violet, gray, white. And they represent the numbers 0 through 9. And these numbers tell us the color codes that are actually, or they tell us the value of a resistor. So let me show you how it works. So the first color is the first number of the resistor value. Second color is the second number. And the third color is the number of zeros. So let me give you an example. You remember that when we were using resistors with our LEDs, we were using the resistors that had the color code yellow, violet, brown, right? Anybody remember what resistance value those resistors had? 470 ohms, exactly. So let's see how that works. So we said that the first color was the first number. So what color or what number does yellow represent? 4. 4, perfect. So we write down 4. And then what number does violet represent?
7.
Perfect. And then the third color represents the number of zeros. So in this case, brown represents 1. So that means that we put 1 0 at the end. So that's how we got 470 ohms from yellow, violet, brown. Okay? What would this have been if we had made, we saw a resistor that was yellow, violet, and then red? Well, the yellow and the violet are still the same, so the first two numbers are still 4, 7. But now, what number does red represent? 2. So there's 2 zeros afterwards, so it would be like this. So that's a 4,700 ohm resistor. Okay? Does that make sense? Okay, let's do another one. Let's say that we had a brown, black, red resistor. So what number is brown?
0.
Perfect. And what number is black? 0. And red is what?
2 zeros.
2. So we'll put 2 more zeros at the end. So this is a 1,000 ohm resistor. Okay? Is that starting to make sense? There's one other number which is, or one other color band which is labeled on a resistor. And that band is called the tolerance band. So let's talk about that for a minute. The tolerance band could be gold, silver, or there might be no tolerance band. So a gold band represents a 5% tolerance. A silver band equals 10% tolerance, and no band represents 20% tolerance. Does anybody know what tolerance means? Yeah, plus or minus. It's how close the actual value has to be to the labeled value. Because if you measure something, in reality, if you can measure something, you'll find that no resistor is ever 1,000 ohms. If you measure it precisely enough, you'll find that it's never exactly 1,000. It might be, 1,100, or a better one might be 1,001, or a really good one might be 1,000.000005 or something. But it's never going to be exactly this number. So what the manufacturers do is they tell you the approximate value, and then they tell you how close the actual value has to be. So let's do an example. Let's say that we had a resistor that was labeled brown, black, red, and then it had a gold band at the end. So gold band means 5% tolerance, right? So that means that the actual resistor has to be 1,000 ohms plus or minus 5%. So what is 5% of 1,000? 50. So this has to be 1,000 plus or minus 50 ohms. So the actual value of the resistor has to be somewhere between, so what would be the lowest value that we could have with this resistor?
50.
Yeah, we could subtract 50, so that would be 950 ohms. And what would be the greatest value we could have? 1,050. So if we saw a resistor that was labeled brown, black, red with a gold band on it, we wouldn't know the exact resistance, but we would know it had to be somewhere between 950 ohms and 1,050 ohms. Okay? Questions about that? Yeah.
So all this measurements is only in ohms. It doesn't go kilo ohms, mega ohms, or there's no such a resistance with such a restriction.
Sure. There are. So that's a good question.
You can add a lot of zeros, but it's going to be easy to read. I mean,
Right. So you are talking about kilo and mega, and there's giga and other prefixes. And these prefixes, we'll learn about them in a little while. So we'll talk about them more. But for now, what these prefixes mean is that they're just a shorthand way of writing big or small numbers. So basically engineers are lazy, okay? That's what it comes down to. We don't like to write out lots and lots of zeros, either at the end of a number or 0.000005. We don't like to spend all that time writing out all those numbers. So instead of writing out lots of zeros, we use these prefixes to indicate that there are lots of zeros. So if we use a prefix of mega, that means that we're talking about millions. So that would be 6 zeros. So if you were talking about 6 mega, or say 3 mega ohms, that would be a 3 followed by 6 zeros. So the prefixes are just ways of indicating that there are lots of zeros without having to write out all those zeros. So yes, we could talk about larger resistors. So let's do an example of that. Let's say that we had red, and then yellow, and a silver tolerance band. Okay. So let's figure out what the range of values could be for that resistor. So what is red? 2. So we got 2, and then 2, and then yellow is 4 zeros. So that's 1, 2, 3, 4. And then silver is 10%. So so this is 220,000 ohms. Another way of writing that would be 220 kilo ohms. Kilo stands for 1,000. So that's some place where we could use the kilo prefix. But you don't have to. And you don't have to understand that yet. That's something that we'll see later on. Okay? So then, what would be 10% of that? 22,000, I think. So plus or minus. So if we subtracted 22,000 from 220,000, we would get, now I made the math hard on myself, right? 198,000, right? That'd be the lowest value that we could have. And if we added 220 on, what would we get? Yeah. So if we saw a resistor that was marked red, red, yellow, silver, we would know that the resistance values could be somewhere between 198,000 ohms and 242,000 ohms. Okay?
Big tolerance.
Yeah, it is a pretty wide tolerance. Yeah. So what are some reasons why you might want to have a tighter tolerance, like a gold band or something like that? Yeah, it's more specific. Exactly. So if you know that you need a resistor that's very specific value, you might choose one that had a gold tolerance band. Yes?
Would there be a benefit into choosing a wider tolerance? Because wouldn't it make more sense to be specific always anyways? Just so if you know what your target resistor you're looking for.
Right. Yeah, so that's a good question. So if you know that you want a specific resistor, why would you put a bigger tolerance on it? Anybody got any ideas? Cost. Exactly. The less precise the resistor has to be, the less money it costs. So if you have something like a little light and you just have to limit the amount of current that's going through there, and you don't care exactly how bright it is, then you might opt for a lower tolerance that will still get you in the ballpark, but will cost a little bit less money. Now, resistors are very inexpensive to begin with. They're a penny or less each. So it doesn't seem like, even for the 5% ones, it doesn't seem like trying to save money there would be really important. But if you're making, you know, thousands or millions of parts, then sometimes it can start to add up. You can just shave off a little bit extra. So yeah, that's really what it comes down to, is cost. Yeah. Any questions about that? Okay. So that's a little bit about resistors, and that's a little bit about color codes. So the other thing I wanted to talk about was a way to remember these color codes. Now, we're not going to force you to memorize the color codes. You can have a sheet of paper with you that has all the colors on it when you're doing a midterm or anything like that in this class. So you're not going to need to memorize the colors. But if you go out in the field and you start using resistors a lot, you'll find that it's helpful to have the color codes memorized, because it'll just be faster for you. So there is something called a mnemonic device, which is a silly way of remembering something that is hard to remember. So the mnemonic device, there are many out there, but the one I like is Bad Boys Place Our Young Girls but Violet generally wins. Okay? So the first letters of these words correspond to the first letters of the colors. So if you can remember this phrase, then you can remember the color code. And that can just speed things up for you. Okay?
Question. If you were to connect two resistors together, will that make the, like it goes through the first resistor, then it, makes it less, the current? And will it make it more or less with the second one, or will it be the same, or?
Yeah, that's a great question. And that's actually what we're going to talk about for our entire next lesson. So that's called series resistance. So what happens is that when you have two resistors in series, the total resistance is the sum of the two resistors. So if you had a 470 ohm and a 1000 ohm in series, then they would act like a 1470 ohm resistor.
Make it smaller, doesn't matter?
Yeah, that's what we're going to spend the next lesson on after that. So, right, parallel is when two resistors are side by side. And what happens then is that the total resistance actually goes down, believe it or not, because the electricity now has two different paths that it can go down. So it's easier than traveling down either single path by itself.
Makes sense.
Yeah, so it's kind of funny. And then, just to blow your minds a little bit more, after that we're going to talk about circuits that have series and parallel components to them. So yeah, it's going to be cool. But we'll spend a little bit more time on that later on. Okay? Other questions? All right. Cool. So that's what I wanted to say about resistors. So let's talk a little bit about meters. Okay? So this is a digital multimeter. There are many different kinds out there, but this is the one that we're going to use. And digital multimeters are mostly pretty much the simplest type of measurement equipment that you can use in electronics. They're also the most widely used. So this is a tool that you're going to be using day in and day out if you go out and actually work in the field of electronics. It allows you to measure many different aspects of a circuit. So this will measure voltage, it'll measure current, it'll measure resistance, the three main components that we've talked about so far. And it'll also do a lot of other measurements as well. It'll measure capacitance, which is something we'll discuss later on. It'll measure inductance, that we'll talk about later also. It'll even measure frequency. So if you have a signal which is alternating at a defined rate, you can hook the meter up and figure out how quickly it's changing, how many times per second. Okay? So these meters are very, very versatile. They're very important. They're probably the tool that you will use the most if you go out and work in electronics. So we're going to start learning how to use them today. And like I said, this is really cool because starting from now, you don't have to believe anything that I say. You can actually go out and see for yourself. Okay? That's what I always liked about electronics and working in the field, is that you could actually test things out and see how things work for yourself. So this is where the experimentation really can get going for you guys. You can try things out, see how they work, and actually see the measurements right away. Okay? So that's a little bit about what meters are and why we care about them. So let's go on and actually talk about what we're going to do in lab today. So one thing that we're going to do in lab is that we're going to measure resistance. So you guys are going to get a bunch of little resistors that look like this. You're going to look at them and actually write down the colors that are in the color code, and then you will actually measure the resistor with your meter and check to see whether the resistor value is what is labeled on the resistor itself. So for instance, if you saw a 470 ohm resistor, you could measure it and see how close the actual value was to 470 ohms. Okay? So that's one thing we're going to do. We're going to measure the resistance. Then we're also going to check some cables. Okay? So this is, everybody's going to get a cable that looks like this. This is a Cat5 cable. Anybody heard of a Cat5 cable? A couple people? If you have Ethernet in your house, then you probably used a Cat5 cable. This is the kind of cable that connects your modem to the wall, or your computer to a modem, or one computer to another computer. It's a networking cable. It stands for Category 5. So this is a pretty standard type of internet connection cable. Okay? So the cable has 8 different wires, and they're all color-coded. So what you want to check is that you want to make sure that the orange wire on one end is connected to the orange wire on the other end, right? If it's connected, then that's good. If it's not connected, then we say the wire is open. There's a break between the one end and the other, so there's an opening between one end and the other, so we call that an open circuit, or an open wire. We also want to make sure that the orange wire is not connected to the brown one, or the blue one, or the green one, or any of the other ones, right? The orange one should be connected to orange and only orange on the other side. If the orange wire is connected to the green one, for instance, then we say that there is a short circuit, okay? So we're going to be checking the cable and looking for open circuits or short circuits. And we're going to use the meter to do that. So let me show you how this works. The first thing we have to do is that everybody's going to have to get a meter and a pair of cables. And we're going to have to connect the cables to the meter. The way that we do that is that, first of all, we put the black meter in the hole that says common. The black wire always goes in the hole that says common. Okay? So no matter what type of measurement you're making, the black wire always goes in the hole that says common. So that's the first thing that we're going to do. The second thing we're going to do is we're going to take the red wire and put it in the far right-hand hole. Right above this hole, there's a little mark that shows the omega symbol. Remember, that's the symbol for resistance. And what we're really doing when we're checking for connection from one side to the other is we're checking the resistance. If there is a connection, from one side to the other, it will have a very, very low resistance, almost 0 ohms. Okay? If there is no connection, then it will be a very, very high resistance, in the millions of ohms. So when we're checking connections, we're really checking resistance. So we put the red wire in the hole, which is labeled resistance. You guys with me so far? All right, so we've got our meter, we've got our cables plugged in. Now we're going to turn the dial and put it in the setting to measure connectivity. So that's this setting, it's almost near the bottom. It's in the resistance measurement quadrant here. This bottom left-hand quadrant is measuring resistance. And it's all the way down. It's labeled 200. And then it's got this little symbol. So it's like 200, and then it's got this symbol. And this symbol is supposed to represent sound. The reason for that is that when you have a good connection, the meter makes a really high-pitched, annoying beeping sound. You guys hear that? All right, so no connection, no sound. Good connection, you get this high-pitched beeping sound. Okay? So we're going to use that to test out our cable. So we're going to grab onto one side of the orange wire with one of the cables. We're going to grab onto the other side with the other cable, and we get a beeping sound. Okay? So it should make a good beeping sound. I think I just don't have it connected very well. Yeah, so anyway, so it's beeping. So we get a good connection on our orange wire. Okay? So we would then go to our lab book and write down that there is a connection from one orange wire to the other one. The next thing we would do is we would connect one side to the orange wire, and then on the other side we would touch all the wires except for the orange wire. Okay? So we touched every wire except the orange one on the other side, and then we listen for a beeping sound. And if we hear a beeping sound, then we know that there's a short in there somewhere. Okay? So we know that this orange wire is shorted to one of the other wires. So then we have to go through each wire by itself and figure out which one it is. Okay? So in this case, it looks like the orange wire is shorted to the orange and white wire. Okay? So then we would mark down that there is a short circuit in there between orange and white. Okay? So we would make that notation in the book. Yeah?
You know that because the beeping sound is a little bit weaker?
Well, no, because there is a beeping sound at all. If there was no connection, there would be no beeping sound.
Okay.
So we want no connection between the orange wire and any other wire.
Okay.
So if there is a beeping between the orange wire and some other wire, then you know that there's a short circuit there. So you're going to go through and you're going to do that for each different color of wire in the book. Okay? And you're going to write down the results in the book. And each cable has a number on it. So this cable has a number 5 there. So you're going to write down the number in your book also. We have a little cheat sheet that tells us which wires are short-circuited and which wires are open for each cable number. So when you guys are all done with your labs, we'll come around with our cheat sheet and make sure that your measurements match up with our recorded values and check you guys off. Okay? So that each cable is a little bit different. Some of them have shorts, some of them don't. Some of them have open wires, some of them don't. So you guys will have to go through and actually test out your own cable and see what it's like. Okay? So that's how we're going to check out the cable. Any questions about that? Yeah.
So just to clarify, open wire means there's like a not a connection within the same wire on each end.
Exactly.
And then a short would be some signals going to another wire.
That's right. And one thing I wanted to mention, the book is a little bit unclear. Okay, so in the lab book, they have this list of wire colors. This is on page 48, if you have the book. So you'll notice that the first line says white/blue, and then the second line says blue/white. Okay? So you should leave the first line just the way it is. The second line, you should cross out the white. Okay? So the first line, where it says white/blue, that'll correspond to the cable, which is white with a blue line on it. The second line, you cross out the white. The second line is just the solid blue wire. Okay? And then the same goes for all the rest of the pairs. So the third line will be white and orange. That'll be the white wire with the orange stripe. And then the fourth line, you'll cross out the white. So the fourth line will just be plain orange. It'll be just the orange wire. Okay? Does that make sense? And you'll do that for the rest of them as well.
Well, the other side.
Yeah, same thing on the other side. Yeah. Other questions?
So to draw all the lights.
So on line 2, 4, 6, and 8, you'll cross out the white. Yeah. Okay. So then the last thing that we're going to do in lab is that we're going to measure actual resistance values. So I brought along a couple of resistors to try out here. Okay, so let's try this one. This one is a yellow, violet, brown. And then it has a gold tolerance. So what number would this be? Yeah, so it's 4, 7, and then 1, 0. So it's a 470 ohm. And then what is the gold tolerance?
5%.
5%. So 470 ohms plus or minus 5%. So what would be 5% of 470? Okay, so that would be plus or minus 23.5. So if we had 470 minus 23.5, what would that give us? 6.5, okay? And that goes up to 493.5. So this is the range that our resistor value should fall into. If it's within this range, then we say that the resistor is in tolerance. If it's somewhere beyond this range, then we say that the resistor is out of tolerance, or it's a bad value, bad resistor. Okay? So let's measure it and figure out what the value actually is. So the way that we're going to measure it is we're going to clip one side of the resistor in one of our leads and the other side of the resistor in the other lead. Okay? we're going to leave the leads in the same place in our meter, because remember this hole on the right is for measuring resistance. And then we're going to have to put this dial into one of these locations in the resistance measuring quadrant. So there are many different locations here. If we look at it, there are different values. So down here, it's 200, and then up there, the next one is labeled 2K. Remember, yeah, K stands for kilo, which is 1,000, so that's 2,000, right? And the next one up is 20K, or 20,000, and then 200K, 200,000, and then it goes up to 2M. What do you think M stands for?
Mega.
Yeah, mega, or million. So this is 2 million. Okay, so these are different places where you can put the dial. Each spot, the number represents the largest resistor value that can be measured in that setting. If you put the meter in a setting and the resistance is larger than that value, the meter will read overload, or OL. So that's what's happening here. I've got the meter down here in the 200 ohm setting. That means it can measure anything up to 200 ohms. But I'm trying to measure a resistor that's about 470 ohms. So the meter says, oh, that resistance is too big for me to sense. I can't tell what it is, so I'm going to give you this indication, OL, overload. Okay? So that's just saying that the resistor is too big to be measured in the current setting. So what you want to do is you want to turn the dial up until it's in the number that is the smallest number, which is larger than the value you're trying to measure. Okay? So in our case, that would be 2,000. So we turn it up, and then this gives us a measurement that says 0.468 K ohms. Now we really haven't talked about kilo ohms yet. We haven't discussed it in any detail, but we just briefly touched on it, and we said that K stands for 1,000, right? So what this means is we have 0.468 times 1,000, and that's how many ohms we have. So what's 0.468 times 1,000? Yeah, so 468 ohms. So is that resistor in tolerance? Yeah, it falls between 446 and 493. So this resistor is in tolerance, and it's a good resistor. Okay?
It's almost perfect.
Yeah, very close, right? It's supposed to be 470, it's 468. So pretty darn close. Yeah?
Do resistors have tolerance with age?
If they get too hot, they can degrade and things like that. The temperature can also affect the resistance. So it might be, 468 at room temperature, but then as it gets very hot or very cold, the resistance value might change. I'm not sure. I don't know whether the resistor actually changes value with age. There are many different types of resistors, so I think that some of them are more stable and some of them are less stable. Yeah. Other questions? Okay. All right, so that's how we're going to use the meter to measure resistance. And we're going to do that, you guys are going to do that for 5 different resistors. Okay? You don't even have to figure out the tolerance band and all of that stuff. All you guys are going to have to do is you're going to look at the colors and then write down the value according to the color. So you would look at yellow, violet, brown, and you would write down 470. And then right next to it, you would write down the measured value. So in this case, you would write down 468. Okay? So you'll do that 5 different resistors. And that's the end of the lab for today. Any questions about that? Okay, then I will take attendance and then I'll let you go.